So sometimes we encounter equations which are non-exact. Okay, so what do I mean? Of course, when for the exact equation we know that. So let me write a general form of an equation. So this is the general form of an equation in the differential form m. So m dx plus n dy. Okay, where m and n are some functions in x and y. So if this we know that this equation is exact, then when partial m over partial y is equal to partial n over partial x, okay, then it is exact. But if not, then it is, of course, it is non-exact. So for the exact, we know that there is a procedure, then you can find the solution. But if it is non-exact, then we cannot use that procedure to find the solution. So what we can do in that case? So in many cases, but not in all cases, we can find such a function uh, which we can multiply to this given non-exact ordinary differential equation. Okay, so for example, let's suppose that that function is called mu. Okay, mu some function in x and y. Okay, so we need to find that function in x and y. So when that mu function is multiplied by this equation, then that equation becomes exact. Okay, so that means it will be mu, so partial derivative of mu times m over with this of y, then that will be equal to the partial derivative of mu times n for x. Okay, so it means that then that differential equation will be exact. Okay, so when we can make that non-exact equation exact, then we can follow the same procedure to find the solution of the differential equation, because that will be a multiplication over here. So the solution of that multiplied equation will be the same as the solution for the original non-exact ordinary differential equation. So now the question is, how do we find it? Okay, well, it's good that we can multiply it with mu, but how do we find mu? So for mu, I think we can use some approach to find it. Okay, so for that approach, we need to find mu by one of the two channels. Okay, so by the first channel, we determine a quantity. Maybe we can call that quantity as p. Okay, some function p of xy. So that function, some function p of xy will be equal to 1 over n partial m over partial y minus partial n over partial x. Okay, so that means these originally partial differentiation, their difference you take from m to n, and then divided by the function n, and then if that if that expression is simple enough, then we can integrate it. In this way, exponent, that means e power, integrate in this way, e power the integral of p xy dx. Okay, remember that in most of the cases, I mean in ideal situations, this function p will be either a function of x or y. Okay, so if it is a function of x, we can differentiate with respect, we can integrate it with respect to x. If it is a function of y, then we can integrate it with respect to y to find that multiplication factor, or we normally call as the integrating factor. So either this approach, or we can find another function qxy, which is simply, instead of 1 over n, it will be 1 over m. Okay, that will be partial n over partial x minus partial m over partial y. That means inverse of this function, negative of this. Okay, so in this case we can get a function of q, and by the same way we can find mu. Sorry. Mu x of y exponent of integral q x of y x xy dx, or it can be either dx or dy. Okay, well, I just take maybe over here as dx only. So either of these things may work out. Sometimes it happens that the expression from the first expression of p from the first such formula is a little bit complicated, then you can use the second one. Okay, so in most of the cases either of these two approaches will work, and then we can easily find this vector mu over here. Okay, so perhaps and then once we find mu, then we can multiply it with mu, and then the remaining procedure is the same as for the exact equation, because after multiplying mu, it is the expression, this original ordinary differential equation will become exact. Okay, so let's do it with the help of one example. Okay, so let me write down the example over here. Xy dx plus 2x square plus 3y square minus 20 is equal to dy. So actually with this equation is probably not the separable equation, and we can also check that it is also not an exact equation. So this is m, this is n, so you can take partial m over partial x equal to, oh sorry, we have to check it by partial m over partial y. So that will be actually our function p. Okay, partial m over partial y, so it was the xy, so with respect to y then it will be x only. Okay, and then partial n over partial x is equal to, so we are differentiating with respect to x, so it will be 2x squared, so it will be 2 times 2, 4x. Okay, 4x, and then y square, it will be 0, 20, it will be 0. So now we can see that partial m over partial y and partial n over partial x are not equal to each other. One is x, another is 4x. Although we can see that there is some they are different, but not much difference, not much different. But it means that there may be something which we can find out that can multiply it and then multiply this equation, and then we can make it exact. So for this thing, what we do is, so we say that this is a q function. No, this is not q, sorry. So we find first maybe p. Okay, p is, what is p? Yeah, is this 1 over n, and then this. So 1 over n is this one. Yeah, so this does not look good. Okay, 2x square plus 3y square minus 20 times partial m over partial y. Okay, so x minus, and then 4x. Okay, I think this is not going to help us, because in this way we will get an expression minus 3x over this, and then if you want to integrate it like this, then this will not work out for us, because this is a relatively complex expression both in terms of x and y. So maybe we can try out instead of p, we can try out q. Okay, So what will be q? So what is q? Q is equal to 1 over m. M is a simple over here, relatively simple here. M is this xy, yeah. Xy is relatively simple, and then it will be partial n over partial x, which is 4x, and then that is x. So this looks to be much simple, so that makes it x cancels with x, so it is 3, so it means 3 over y. Well, that is good, that is good enough. So now we can find the integrating factor. Okay, integrating factor is the exponent, okay, of integral 3 over y, and then since this function is in terms of y only, so it is better to integrate it in terms of y. Okay, we will integrate it in terms of y in this case. Okay. Yeah, yeah. So we will integrate it with respect to y. In fact, I think I just did some mistake. I think for these integrating factors, so first will first option you will integrate it with respect to x. In the second option you will integrate with respect to y, and it will be likely that situation in all the questions. So this integrating factor can be found from here. So we can see that exponent 3 over y, so it will be 3 log of y. Okay, there is no need to add the constant of integration in this case, because we are using it as an integrating factor, not for the final answer. So it will be 3 over y, integral will be 3 log of y, and further if we simplify it, exponent 3 log of y, so you can represent it like log y cube, and now it can simplify it to like y cube. So this y cube will be the will be the multiplication or the integrating factor. So that means the original equation will be multiplied by y cube. Okay, y cube. So if we multiply this original equation by y cube, so it will be xy cube xy power 4 dx plus y cube into 2x square plus 3y square minus 20 dy equal to 0. So now we can check that whether this equation is exact or not. It should be exact. So this will be m, and this whole expression will be n. So partial m over partial y, it will be then xy, so it will be well, earlier it was xy, so it was x. Okay, so now it is 4y 4xy cube. Okay, then partial n over partial x, so it is equal to, because it is y cube, so y cube will remain here, and then it is inside as before, it is 4x. Okay, plus 0 minus 0, so then it is 4x y cube. Okay, so now you can see that the equation has become exact. So we will solve this equation in the next clip.